speed constant from the air to the plexiglass or the water or the diamond or whatever? No, definitely does not. So remember your wave speed equation. V is equal to F lambda, right? For this to change, one of three things has to happen. Frequency could change, wavelength could change, they both could change. But from looking at it, if the color doesn't change, that means the frequency does not change, which means the wavelength does. Okay? The wavelength is different. That's important to us because that's what we're trying to match up anyway, right? We're trying to match up peaks and valleys, which means up here I might have a wave that looks like this. And in here I might have a wave that looks like this. Right? So what I'm saying, for this to be constructive interference, is this has to be, if this is bouncing off with a peak, this has to be leaving with a peak. To match that up, I've got to figure out how the wavelength operates in here. Right? The good news is it turns out to be a function of the index of refraction, which is usually something you can look up pretty simply, or usually something that would be given to you. Here's a better graphic of what I'm talking about. Maybe better, maybe more confusing, I don't know. So, you can see what's happening in here. I have a wave coming in with a certain wavelength, and then in the medium, it changes to a different level. This inverted stuff we'll talk about in a second. Don't worry about that for now. What I'm pointing out is that it's got a different wavelength inside than outside. But then, of course, when it moves back outside, I get my old wavelength back. Right? The wavelength shifts again because the speed changes again to the speed of light and air. And so I've got to take that into account. Right? So the way I do that is by, and I'm not going to go through the algebra for this. It's in your book if you're interested. Talking about the wavelength in the medium as lambda n, which you can match up to the wavelength outside by this lambda in air over the n of the medium. So this is a really simple formula. But this tells you the wavelength in the medium. You just take the wavelength in air and you divide it by the wavelength of the medium. So in the case we have here, I don't expect you to remember, but water has an index of refraction of about 1.33. So if this is, I don't know, 600 nanometer light in air, in here it's 600 nanometers divided by 1.33. So this actually turns out to be okay. Because this is where we're trying to match it up. All right, so that's the first complication. This is lambda in the medium, because that's where the path length difference takes place. But lambda n is usually findable, no big deal. Okay. Now, before any questions about that? Okay. So the other complication that comes from the fact that we haven't talked about yet, till now, is that when a wave is reflected, there is a possibility for a phase inversion, right? What does that mean? It means a peak could become a trough, right? The upshot of this is here. If a wave reflects from a slower medium its phase is inverted. All right, what does that mean? How does that work out for us? Okay, to see why this is important, let's remember originally when I was drawing waves on the board and moving their sources around. So I had one wave which looked like this, and then I had another wave which I started backward, back here, and instead looked like this. So I have something generating these two waves. What sort of interference do I get here? Destructive, yes. So the path length difference here is a half integer multiple of the wave. Okay? Which is what we've been saying. Half integer multiples lead to destructive interference. Okay. Well, here's the wrench in the plans, right? I have a switch on this wave generator that if I flip the switch, all of a sudden it starts producing a wave that looks like this. Right? So if I invert the phase of this wave generator, now I've got this situation where a half integer multiple produces constructive interference, right? That's the problem. So the reason I didn't write down which is constructive and which is destructive is because you have to figure out if you have phase shifts. You have to figure out if you flipped any switches. Furthermore, you could flip a switch twice, right? You could have an inversion at the top and an inversion at the bottom, which means you flip it at the top and then you flip it back at the bottom, which basically means you haven't flipped it at all. So here's how you do it. If a wave reflects from a slower medium, right, what does that mean in terms of the index of refraction? Remember, the higher the index of refraction, the slower the wave speed. So if it reflects off something with a higher index of refraction than the medium from which it was propagating to begin with, it flips the phase. So